Example 7.3, testing the conditions of static equilibrium, is on pages 242 and 243. It says, place the ends of a standard meter stick on two scales, as shown below. The scales each read 0.50 newtons. From this, we infer that the mass of the meter stick is about 0.10 kilograms, which you could take a newton divided by around 10 newtons per kilogram, 0.1 kilograms. Predict what each scale will read if you place a 5 kilogram brick 40 centimeters to the right of the left scale. So now that's what I have drawn, is we've got a scale, two scales, we've got a meter stick, and then there is a brick right here, and then the brick is not centered. This is showing the center of mass of the meter stick right there, and there's our brick. So we know that it's a meter long. We know that since it's a evenly distributed mass, that the center of mass would be right in the middle at 50 centimeters. We're told the brick is 40 centimeters away from scale 1, and we need to figure out what would the scales read. We can, and what I will do is I redrew this just looking at forces. So this again right in the middle is my meter stick. I've replaced the physical objects with force arrows. So we've got the normal force of the left scale on the stick. We've got the normal force of the right scale on the stick. We've got the normal force of the brick on the stick. And then the force of the earth on the stick, basically the weight of the stick. And we've got those distances now in meters. Something that I wanted to remind you about was torques and clockwise and counterclockwise, positive and negative. So one way to do this problem is to pick one of the ends as your axis of rotation, where imagine that's where it's pinned down and everything is going to circle around that point. So we're pinning down the left side of this and everything's going to circle around that point. So if this was pinned here and we had a downward force, that would cause a rotation somewhat like this, what I've drawn in green. If you use the right-hand rule, curl your fingers around in that path, your thumb is pointing away from you. That would be a negative or clockwise. Same thing with this one. If you go down with your fingers, the way it would curl, thumb is away from you. So I have both of those marked as a negative torque. So if the scale is at static equilibrium, where everything is balanced, we know that there is going to be some certain things that have to be equal to 0. If we took, and I'm going to make that black. If we took we added up all the forces, the sum of those forces in the x direction are going to have to be equal to 0 for everything to work out. Same thing if we add up all the forces in the y direction. So the sum of the forces in the y direction have to be equal to 0. It's not going to go left and right. It's not going to go up and down. The other thing it's not going to be doing is rotating unnecessarily. So the sum of all the torques have to be equal to 0. As far as the sum of the forces in the x direction, that's pretty easy. We don't have any forces in the x direction. We only have these red forces in the y direction. So as far as the red forces in the y direction, all those things that are in red have to equal 0. And with our y direction, up is positive, down is negative. So we've got the weight of the stick itself, the force of the earth on the stick. I have that negative because that is a downward force, and we're establishing that down in the y direction is negative. There's also the normal force of the brick on the stick, which I would say is the weight of the brick. For whatever reason, the book uses normal force of the brick on the stick. I don't know, it's hard to say. B on S. So those are our two downward arrows. We've got to account for our upward arrows as well. The normal force of the right scale on the stick plus the normal force of the left scale on the stick. All of those have to be equal to 0. So this equation that I just wrote is to sort of satisfy this condition that all the forces in the y direction have to be equal to 0. X direction, that's done. There are no forces in the x direction. We also are going to have an equation that takes care of this torque issue, because we've got a positive torque and a negative a couple negative torques. They got to end up equaling 0 as well. So I'm going to write an equation that goes with the torques. And a torque is a force times a distance. So if we're talking about the same torque here, earth on the stick, we'll go in the same order. We've got the force of it, force of the earth on the stick. I squished that way too much. Force of earth on stick times the distance from the axis of rotation to the force. So it's that force times, in this case, the distance is 0.5 meters. There's also going to be a negative force of the brick, normal force of that brick on the stick. That, from the axis of rotation, is 0.4 meters away. There is the normal force of the right scale on the stick. That would be a full meter away from the axis of rotation. So normal right scale on stick times 1 meter. And as far as the normal forces of the left scale on the stick, that does not provide a torque. Really, I should have this arrow in the exact same location as the axis of rotation. Maybe it should look more like that. But since there is no distance, there is no torque. It'd be like if you're trying to open a door. If you push on the outside of the door, it will open. If you push directly on the hinges, it's not going to open. You're just pushing on the hinges because you don't have any, you're not applying it over a distance from that rotation point. So all of these torques have to also be equal to 0. So we've got two equations for two different situations. I don't know where the green went. That's okay. So this is going to satisfy that situation. What we're going to have to do from there is first, I guess, solve for what we know, and that's the weight of that meter stick. So we know that the meter stick, the force of the earth on that stick. Time out, I'm going to do the brick first. Earth on the brick. Okay, that is super confusing because it's here it's listed as force of earth on the brick, and we really mean the same as this. What's normal? I'm just going to make it normal then.
That's what it did in the book. It did switch it up?
Yeah.
I think they messed up.
They also switch up a lot between 9.8 and 10 out of nowhere. Yeah. Normal force of the earth on the book is going to be equal to, I said earth on book, and it's totally not earth on book. It's earth on brick, and I erased it for no reason because I'm having a rough time here. Is the mass of the brick times gravity. Well, we have that our mass of our brick is 5.0 kilograms, was from the word equation part of it, times our gravitational field constant of 9.8 newtons for every kilogram as long as it's on Earth. So our brick weighs 49 newtons, provides a force of 49 newtons. With that in mind, we can go back to the torque equation and think of it as right side and left side. Now I have to remember. For now, we're going to ignore the left side because that's our axis of rotation. I should draw another arrow. What I'm really doing is taking this situation yet again, but I'm going to put some more numbers in because we have some of these numbers on our initial thing. We've got masses of sticks, and we're just trying to find out the normal force. But we know how heavy the brick is, we know how heavy the stick is, and we can use these to solve for what we don't know. Clickety click. So we have the mass of the stick itself, so force of the earth on the stick. Or we actually, I'm actually looking at this one. That's my bad. Having an off day. That's okay. It's a Monday after a break. We're just trying to survive. Don't know why colors don't change. That's okay. So negative force of earth on stick. We had that as a mass of negative 0.10 kilograms. We're taking that times gravity because we're going from kilograms, mass, to weight, which is newtons. So we're taking that times 9.8 newtons for every kilogram, which that didn't turn out the best either. That's okay. Those two together are going to be our force of the earth on the stick, taking mass times gravity. Because it's torque, we have to take those multiplied by the distance. The distance in this case is 0.50 meters. Mass of, or I should say force of stick, distance of stick from rotation point. Okay. Minus this stuff, normal force of brick on stick. That would be this stuff, 5.0 times 9.8. Really, I don't know why I did that separately. Really didn't need to do that. 5.0 kilograms times 9.8 newtons for every one of those kilograms. We've got the normal force of the right side on the stick. We don't know what that actual value is yet. As far as the brick, I forgot to put that this would also be 0.4 meters. So we've got the torque in the middle of the stick taken care of, the torque at the brick taken care of. We don't know everything about this, but we can write down what we do know, pretty much repeating it. Normal force of the right scale on the stick has to be equal to 0. So we only have one unknown in there, and that is the normal force of the right scale on the stick. You would go through the algebra, you'd have this term, you'd combine those terms, get it to the other side. We end up with that the normal force of the right scale on the stick is equal to 20.5 newtons. So that means that is what that scale is going to read. Scale number 2 would be 20.5 newtons. One last thing we don't know about the left scale. So with the left scale, we can take what we found out here with our right scale and apply it to the left one. So left side, we've got that same, actually, to find out about the left side, we can't use the torque equation because there is no torque on the left side because that is the axis of rotation. So we have to go back to this one, which this had to do with the forces only. This was just the sum of the forces in the y direction. That's what we're going to use. This was the sum of the torques down here. That's your force times your distance. We don't have that for the left side. So we're going to take what we know and apply it back to the sum of the forces in the y direction. So we've got the force of the Earth on the scale. We know that that is 0.10 kilograms times 9.8 newtons per kilogram. And we know that it's negative because it's a pointing down. We've established that down is negative. We've got this, the normal force of the brick on that stick. We're also going to call that negative because it's downward. We know it's a 5 kilogram brick, and we know that it's 9.8 newtons for every one of those kilograms. For the normal force of the right scale on the stick, we just calculated that right here from the torque equation. That is a nice check mark. We can just plug that right in, so plus 20.5. We have it as 20.5 because that is an upward one. This is what we're solving for. We want to know then plus the normal force of the left scale on the stick. We're just going to keep that as it is. We don't know yet. All that has to be equal to 0. Like before, you're going to have to try to calculate and solve for this particular unknown. When you solve for that particular unknown, we get that the normal force on the left side, or I'm sorry, the left scale on the stick is 30.5 newtons. So that means that this scale would read 30.5 newtons. And it should make sense that this scale would read higher than that scale because the brick is off center. It's more towards scale number 1.